Welcome to Debug Log, software engineering war stories, architecture decisions, and lessons learned the hard way. Let's dig in. A 9-year-old bug, 10 lines of code, discovered by an AI-assisted scanner. It's a paradox of modern software engineering.
Indeed, the copy-fail exploit in the Linux kernel's page cache represents a blend of subtlety and persistence that challenges common assumptions about code security and review.
So a decade of eyeballs, human and automated, missed something this small, yet potentially so critical, sitting right there in the core of the operating system?
That's the crux of it. The phantom aspect isn't just a clever title. It speaks to how deeply a flaw can be embedded and how difficult it can be to detect without novel approaches.
Focusing on the exploit itself, the 10-line copy-fail exploit, when one hears 10 lines, what does that immediately suggest about the nature of the vulnerability?
It suggests surgical precision. Many exploits are complex, involving multiple stages, memory gadgets, or intricate race conditions. A 10-line exploit, especially one targeting the kernel, implies a very direct, potent manipulation. It's not about brute force or a long chain of events. It's about hitting a specific, critical point with minimal code. Think of it like a perfectly aimed, tiny projectile disabling a major system.
It doesn't need to be large to be effective if it strikes the right spot. So it's not a matter of a massive buffer overflow that requires pages of shellcode, but something far more elegant, almost like a single misplaced comma in a vital instruction.
Precisely. It likely exploits a very specific misunderstanding or misconfiguration in how data is handled or synchronized. The copy-fail part points to a data integrity or memory corruption issue during a copy operation. In a kernel, a copy isn't just moving bytes. It involves memory mappings, permissions, and sometimes interaction with hardware. A failure in that process, even a transient one, can be catastrophic.
And that leads directly to the page cache. For listeners unfamiliar, what is the page cache and why is it such a high-stakes environment for a vulnerability like this?
The page cache is essentially the operating system's fast access memory buffer for files and data. When you read a file, the kernel often loads portions of it into the page cache so that subsequent reads from that file or by other processes are much faster, avoiding slow disk I/O. It's a critical performance optimization layer.
So it's like a highly optimized, frequently accessed staging area for almost everything the system interacts with from disk.
Exactly. And because it's a shared resource, and because it directly handles data that applications and the kernel itself are accessing, any flaw there has profound implications. If an attacker can manipulate data within the page cache, or the metadata associated with it, they could potentially corrupt files, escalate privileges, or even execute arbitrary code in kernel space, effectively taking over the entire system. It's a nexus where user space actions translate into kernel space operations, making it an extremely sensitive area.
A phantom in this critical nervous system. What makes a bug in the page cache so difficult to detect, even for experienced auditors?
The phantom aspect often refers to issues that are non-obvious, transient, or dependent on highly specific timing or system load. Page cache operations are inherently concurrent. Multiple processes might be reading from or writing to the same file, or the kernel might be performing internal maintenance on the cache. This creates fertile ground for race conditions, where the precise order of operations dictates whether a bug manifests. Such conditions are notoriously difficult to reproduce, making them hard to catch in testing or code review. A human auditor might look at the code and see what should happen, but miss the very narrow window where a different sequence of events could lead to a flaw.
So it's not just about looking at the lines of code in isolation, but understanding the countless permutations of how they might execute in a highly dynamic, concurrent environment. That sounds like an impossible task for a human.
It approaches impossibility. The complexity grows exponentially with the number of interacting components and potential execution paths. This highlights the 9-year blind spot.
9 years? The Linux kernel is one of the most scrutinized pieces of software on the planet. It undergoes continuous review by thousands of developers, not to mention a multitude of static analyzers, fuzzers, and security audits. How does a 10-line vulnerability evade detection for nearly a decade in such an environment?
It's a testament to several factors. First, the sheer scale and complexity of the kernel. Even a small bug can hide in plain sight if its trigger conditions are rare or specific to obscure system configurations or workloads. Second, the nature of the page cache itself, as previously discussed. Its concurrency makes race conditions extremely subtle. Traditional static analysis often struggles with inter-process or inter-thread interactions, and fuzzers might not hit the exact sequence of events required.
So it wasn't necessarily a flaw in the code that was obviously wrong, but perhaps a flaw in the assumptions made about how that code would interact with the rest of the system under certain pressures.
Exactly. Or a subtle off-by-one error, a miscalculated boundary, or an incorrect synchronization primitive in a less trafficked code path. It could also be that the bug was introduced in an earlier version of the kernel and then carried forward through updates, becoming deeply ingrained. It highlights that even in a highly mature, open-source project with vast developer involvement, human oversight has limits, particularly in the face of emergent properties from complex interactions. It's like finding a single, perfectly camouflaged snake in a dense jungle that thousands of people have walked through for years.
This introduces the AI-assisted software scan, which could be considered a new approach. What capabilities do these tools possess that allowed them to uncover what human auditors and conventional tools missed?
AI-assisted scanners represent a significant evolution in vulnerability research. While traditional static analysis looks for known patterns or deviations from rules, and fuzzers throw random inputs at programs, AI-assisted tools can operate at a higher level of abstraction. They can leverage machine learning to understand code semantics, predict potential execution paths, and even generate highly targeted inputs designed to provoke unusual system states.
So instead of just checking for a predefined list of bad things, an AI can start to understand the intent of the code and then identify where that intent might break down under specific non-obvious conditions.
That's a good way to put it. They can analyze vast code bases, recognizing subtle patterns that indicate potential vulnerabilities, even if those patterns don't perfectly match known exploit signatures. More advanced forms might use reinforcement learning to explore the program's state space more efficiently than brute force fuzzing. They can learn from previous attempts, focusing their efforts on areas of the code that are more complex or have historically been bug-prone. For a bug like the copy fail in the page cache, an AI could potentially analyze the concurrent access patterns, model the memory state, and identify the precise race window or data corruption path that a human might overlook, due to the sheer volume of possibilities. It's like having an indefatigable, hyper-intelligent detective meticulously sifting through every single interaction, no matter how small, until it finds the one that doesn't quite add up.
This implies a shift in the arms race then. If AI can find these deeply hidden, subtle bugs, does that mean the era of the human-discovered zero-day is nearing its end?
It certainly changes the landscape. AI tools are becoming increasingly adept at finding classes of bugs that were previously in the unknown unknowns category, or those requiring an extraordinary level of human effort to find. This means that the low-hanging fruit bugs are picked off faster, and even the more complex ones become discoverable by machines. For defenders, it's a powerful new ally. For attackers, it means they also have access to these tools, and the bar for finding novel vulnerabilities is being raised for humans. It forces everyone to up their game.
Considering the actual impact of an exploit like this, if someone manages to trigger this 10-line copy fail in the page cache, what kind of damage or access could they achieve?
Given it's a kernel bug, the impact is severe. Any vulnerability that allows manipulation of kernel memory or state typically leads to privilege escalation. This means an attacker starting from a limited, unprivileged user account could gain root access, effectively taking full control of the operating system. With root access, they could install malware, steal data, alter system configurations, or even render the system unusable.
So the copy fail isn't just about corrupting a single file, it's about potentially corrupting the kernel's understanding of its own memory or processes, leading to total compromise.
Exactly. A copy fail in the page cache could mean a misdirected pointer, an incorrect permissions flag being set, or even overwriting critical kernel data structures with attacker-controlled data. This could be used to inject malicious code into the kernel, bypass security mechanisms, or create arbitrary write primitives. The conciseness of the exploit implies a direct path to this level of control, not a roundabout series of actions. The exact method would depend on the specifics of the bug, but the outcome is almost always system-wide compromise.
This is a significant finding then, not just for Linux users, but for understanding system security more broadly. What are the key takeaways for software developers and security practitioners from this incident?
One major takeaway is the enduring challenge of kernel security. Even with decades of experience and massive open-source scrutiny, fundamental flaws can persist. It reinforces that complexity is the enemy of security. Another is the critical importance of memory safety and data integrity, especially in shared, performance-critical components like the page cache. Developers need to be incredibly rigorous in their assumptions about concurrency and memory management.
And the role of tooling?
Absolutely. This incident strongly advocates for diverse testing methodologies. Relying solely on human review or traditional fuzzing is no longer sufficient. The successful discovery by an AI-assisted scanner underscores the need to integrate these advanced tools into the development and auditing pipeline. It's not about replacing human expertise, but augmenting it. The AI found the needle, but humans still need to understand why it was a needle and how to mend the haystack. It also highlights the need for continuous vigilance. No system is ever done in terms of security. It's an ongoing process of discovery and remediation.
So, what is being observed is the perpetual arms race between finding and fixing bugs, just with a new, very powerful contender entering the field.
Indeed, it's a reminder that even the most robust systems are built on layers of abstraction, and sometimes a single, tiny logical flaw can destabilize the entire edifice. The phantom was there all along, waiting for the right tool to reveal it.
This incident prompts the question of how many more of these 9-year-old, 10-line phantoms are still lurking in critical infrastructure, just waiting for an AI to shine a light on them?
A truly precise question. And it also begs the question of whether AI-assisted discovery will become so ubiquitous that the cost-benefit analysis for maintaining highly complex, foundational open-source projects like the Linux kernel will need to be fundamentally reevaluated.
That's a wrap on this debug log. Join us next time for more engineering war stories and hard-won lessons. If any of this hit close to home, subscribe and tell your team.
Ship it carefully.